In continuation with our discussion, so there are only two groups of methods of solution considered. The first one is the direct methods and the second one is the iterative methods. Direct method is the method wherein the exact value of the solution set can be obtained, while iterative method is a method wherein the approximate value is obtained by iteration. What are the methods under direct method? So we have here the Gauss elimination, second the naive Gauss elimination or the forward elimination and back substitution. The third is the Gauss-Jordan elimination. For the iterative methods, we have here the LU decomposition, Cholesky decomposition, Jacobi or the Gauss-Jacobi method. Fourth is the Gauss-Seidel method and the conjugate gradient. Gauss elimination involves combining equations to eliminate unknowns. So although it is one of the earliest methods of solving simultaneous equation, it remains among the most important algorithms in use today and is the basis for linear equation solving on many popular software packages. So there are ways of solving linear equation wherein n is less than or equal to 3. So n less than or equal to 3 means that we are solving small numbers of equations. So 1 will be the graphical method, 2 is the Cramer's rule, 3 is the method of elimination. For our first method, we will have here the graphical method. Graphical solution is obtainable for two equations by plotting them on Cartesian coordinate system with one axis corresponding to x sub 1 and the other to x sub 2. Be mindful na class that we're not going to use the x and y. Instead, we're going to use x sub 1 and x sub 2 in a linear solution. Because we are dealing with linear equation, so each equation is a straight line. So this can be easily illustrated in a general equation. So we will have here the a sub 1, 1, x sub 1 plus a sub 1 2, x sub 2 equals to b sub 1. So this is the first linear equation. The second is a 2 sub 1, x sub 1 plus a sub 2, 2, x sub 2 plus b sub 2. So instead of x and y, so we are using x sub 1 and x sub 2. Thus, the equations are now in the form of a straight line. That is, x sub 2 is simply equal to the slope of multiplied by x sub 1 plus the intercept. So, these lines can be graphed on a Cartesian coordinates with x sub 2 as the ordinate and x sub 1 as the abscissa. So, the values of x sub 1 and x sub 2 at the intersection of the line can represent the solution, both the equation that solves x sub 2. In order to understand more about graphical method, so let's have an example. Example of graphical method for two equations. So, problem statement. Use the graphical method to solve 3x sub 1 plus 2x sub 2 equals to 18 minus x sub 1 plus 2x sub 2 equals to 2. So, our solution will be, so let x sub 1 be the abscissa to solve 3x sub 1 plus 2x sub 2 is equals to 18. It will be in this particular form. So, this is simply rearranging the equation wherein we're finding the value of x sub 2. So, as I've said, we are not using x and y for the linear systems. Instead, we're using x sub 1 and x sub 2. So, x sub 2 is similar to our y value. So, rearranging the equation, we will have here. So, x sub 2 is equals to negative 3 over 2 x sub 1 plus 9. It is now 9 because of the denominator 2 for our 18. So, base and we will have here the x sub 2. So, this is simply rearranging the equation, which when plotted on figure 9.1 is a straight line with an intercept of 9 and a slope of negative 3.2. So, we all know if we have a linear equation, this is simply y is equals to mx plus b. So, b as 9 for the intercept and negative 3 halves as the slope. But we are not using x and y as our linear function. Instead, we are using x sub 1 and x sub 2. This is our figure 9.1. You will see here how we have plotted our first equation. So this is simply, we have the x sub 2 equals to negative 3 halves x plus 9. So simply starting from 0, 1, and 2, we will be able to plot our equation or our function in this form. So this is in a form of a straight line. Second equation, which is the negative x sub 1 plus 2x sub 2 plus 2, can also be solved for x sub 2 in this particular equation. X sub 2 is equals to 1 half x sub 1 plus 1. So this is simply rearranging the equation, which is also plotted on figure 9.1. So the solution is the intersection of two lines is at x sub 1 equals to 4 and x sub 2 equals to 3. So getting back to our previous figure, this will be the plotted straight line of our second equation. I'll have here the function x sub 2 simply by rearranging the equation 1 half x sub 1 plus 1. So graphically, point of intersection or the intersection of two lines is at 4 and 3, wherein x sub 1 is 4 and x sub 2 is 3. So as refer to the orientation or refer to the graphical solution, so we have here horizontally for our x sub 1 and vertically for the x sub 2. So this result can be checked by substituting these values into the original equations to yield the equations. So this is simply from the equation 3x sub 1 plus 2x sub 2 equals to 18, negative x sub 1 plus 2x sub 2 equals to 2. So substituting the values of 4 and 3 to all equation, it should yield the result of 18 and 2. We can also use Excel in applying graphical method. So we have here for the given example, so 3x sub 1 plus 2x sub 2 is equals to 18. Negative x sub 1 plus 2x sub 2 is equals to 2. So for the first equation, we were able to find this particular equation or the rearrangement of the given equation for the first equation, and this is for the second equation. Using the derived or rearranged equation, so we have here negative 1.5 multiplied by the value of 0 plus 9. So simply by copying this out to all the numbers, so we were able to find this result of the function. So we used here step size of 1. So for the second equation, we have here 0.5 times x sub 1 plus 1. So same process, substituting and selecting this cell. And based from this plotting, so the point of intersection is at 4 and 3. So 4 at x sub 1 and 3 at x sub 2. So this is how you use the Excel in applying graphical method. Under uniqueness of solution, a linear system can have 0, 1, or infinite set of solution as shown in the illustration below. So for our figure 9.2, so we have here the graphical depiction of singular and ill-conditioned systems. So the previous example in our graphical method is an example linear system with one solution. We have here figure 9.2. So depicts 3 cases that can pose problems when solving sets of linear equation. So in our figure 9.2a, given the functions, so you will notice here, substituting the values from 0 to a certain value, same with our second equation, you will notice that the result, the two equation represents parallel lines. So the case where the two equation represent parallel lines, so there is no solution because the lines never crosses. So for our figure 9.2b, based on the given two equation, our lines are coincident. So what does it mean? So generally or approximately, the lines are almost the same or they represent the same line. So, coincidence. So, in this situation, there is an infinite number of solutions. For our 9.2c, so both types of systems are said to be singular, B and C. In addition, systems that are very close to being singular as shown in 9.2c can also cause problem, and these systems are said to be ill-conditioned systems. So we have here the no solution, the infinite solution, and the ill-conditioned system. So where the slope are so close that the point of intersection is difficult to detect visually. So we will have here difficulty in detecting the point of intersection or POI. The type of coefficient matrix A can determine the uniqueness of the solution. So this can be done by assessing the singularity of the matrix A. So singular matrix class is a square matrix whose determinant is equals to 0. So if the matrix A is equals to 0, the system has no solution or infinite number of solutions. If the determinant is not equal to 0, the system has one solution. So let's have an example. For the uniqueness of solutions, so problem statement determine the number of solution set of the given system. So we have here the same given equation as our graphical method. So for the solution, calculate or compute the determinant of its coefficient matrix. So this is simply difference of the product of 2 and 3 and the product of negative 1 and 2. So we will have here the result equal to 8. So since our determinant of matrix A is not equal to 0, the system has exactly one set of solution. This is the conventional form of equation. And this is the matrix form. Therefore, our determinants of matrix A or simply finding the determinants of the coefficient matrix. So, this is the coefficient matrix. So, you will be questioning why are we having a mathematical background about matrix notation or our matrix solution or matrix operating rules. Why? Because it will be applied in our methods such as Cramer's rule. So, Cramer's rule solution technique that is best suited to small numbers of equation. Let's have here first the concept of determinant before we apply Cramer's rule. So that is one of the reasons why we have series of mathematical background about matrix and matrix operating rules. So the determinant can be illustrated for a set of 3 equations where shorthand notation of matrix A is the coefficient matrix. So, it is in this particular representation. In connection with the concept of determinant, so the determinant D of the system is formed from the coefficient of the equation as in D is equals to the determinant of the matrix A. So, take note class if we have here. The determinant here is also called a second order determinant. So for this third order case, a single numerical value for the determinant can be computed as these 2 by 2 determinants are called minors. So let's have an example in finding the determinants of the matrix. So let's compute the values of the determinants of the system represented in figure 9.1 and 9.2. If you recall our example in the uniqueness of the solution, so you will notice class, this is the result from our uniqueness of the solution. So we have here the determinant equals to 8, which means class that finding the determinant of the coefficient of the matrix determines the uniqueness of the solution. So we were able to know that the determinant of A is not equals to 0, which means that this has a one solution. So 9.2A, so we have here the result of 0, same as 9.2B. So for our 9.2a, so this means that it has no solution. If you recall figure 9.2a, for our figure 9.2b, so we have here also a result of 0. It has an infinite solution. If our determinant equal to 0, it either has a 2 solution or it has an infinite solution. So, we will have here the 9.2a. So, recalling, so it has a parallel line. Dito naman, coincidence. So, this is referred to as the infinite solution. If you recall our figure 9.2a and 9.2b. So, for our figure 9.2c, so it has a value close to 0. So, it has a negative 0.0 for the value of the determinant of the coefficient. So, it has an ill-conditioned system. So, we have difficulty detecting or visually detecting the point of intersection because it has ill-conditioned system. For the Kramer's rule states that each unknown in a system of linear algebraic equation may be expressed as a fraction of two determinants with the denominator d and with the numerator obtained from d by replacing the column of the coefficient of the unknown in the fraction by the constant b1, b2, and so on and so forth, b sub n. So, for example, x sub 1 would be computed as determinant in the denominator and also obtaining the determinant but replacing a11, a21, a31 with b1, b2, b3, and let's have an example. So for Kramer's rule problem statement, use Kramer's rule to solve the given equation. So we have here x sub 1, x sub 2, and x sub 3. So, for the solution, we can write the determinant D as 0.3, 0.5, 0.1, 0.52, 1, 0.31, 1.9, and 0.5. So, this is simply finding the determinant of the matrix or the coefficient matrix. And continuation of the solution. So, the minors are for A sub 1, A sub 2, and A sub 3. And this can be used to evaluate the determinant as in determinant equals to negative 0.022. And we already have the determinant. So, applying, finding the x sub 1. So, this is simply changing A11, A21, A31 with B1, B2, and B3. So, the solution will be for x sub 1, so ang pinalit natin, so this will now be the b1, b2, and b3. And for x sub 2, what we change is this will be the b1, b2, and b3. X sub 3, instead of using a13, a23, and a33, we use here the values of b1, b2, and b3. And we were able to find the values of x sub 1, x sub 2, and x sub 3 respectively. We can also use our Excel in order to apply Kramer's rule. We have the given here. This is our conventional form. So, we can also represent this in matrix form. And this is how we represent them. So, we have here 0.3, 0.5, 0.1 from the x sub 1. And 0.52, 1.3 for x sub 2, 1, 1.9.5 for the coefficient of x sub 3, and we have here the x sub 1, x sub 2, and x sub 3. So, these are the values of B, B1, B2, B3. So, using the equation, the given equation, so, finding the determinant, simply A11 multiplied by the difference of the product A22 times A33 minus A32 times A23 minus A12 multiplied by A21 multiplied by A33 minus A31 times A23 plus A13 times the difference of the product A21 times A32 minus A31 times A22. We were able to find the value of the determinant negative 0.022. Or we can simply use Excel function. So we can simply type mdeterm, which means finding the determinant, and select the array and simply click enter, and you will also be able to find the value of the determinant. Following the equation, so we already have the value of the determinant, we will be able to find the value of x sub 1, x sub 2, x sub 3. For x sub 1, so we need to use the value instead of A11, A21, and A31, we're going to use the value of B1, B2, and B3. And we're going to use B2. And same with 1 and 1.2. And these are the data that we're going to use for the numerator, and we already have for the denominator. And for the result, we can simply use the function of our Excel. So mdeterm, which means finding the determinant of the matrix, select the array, and simply click enter. And we already have here the value for our numerator. And for our x sub 1, it will be equal to the numerator divided by the denominator. And we will be able to find the value negative 14.9. So for our x sub 2, so we're using the value of A11. So what we're going to change is for this particular value using our B values. So equate, and we're going to use the value at the last column. And for the determinant at the numerator, mdeterm, which means finding the determinant of the given matrix. So we already have for the value at the numerator. So for our x sub 2, simply select the numerator divided by the denominator, which is the determinant, and we already have the value of negative 29.5. And for our x sub 3, so we're going to use these two columns, and we're going to change the third column with our b values. So for our b values, and for the numerator, so mdeterm, select the given array for the matrix. So we already have the value at the numerator. And for the value of x sub 3, so simply select the numerator divided by the denominator. And we already have here the value of 19.8. Getting back with our presentation, so you will notice we also find the value of x sub 1, x sub 2, and x sub 3 using our Excel. For the elimination of the unknowns, elimination of unknowns by combining equation is an algebraic approach and can be illustrated for a set of two equations. It is represented as the same representation for our linear equations. So, for example, our equation 9.6 might be multiplied by a sub 21 and equation 9.7 by a sub 11 or a sub 11. So it will be represented in this particular equation, respectively. So, and subtracting equation 9.8 from 9.9, so you will notice they have the same constant or coefficient matrix. So this will have a 0 value if we subtract equation 9.8 from 9.9. And it will yield the equation a sub 22, a sub 11, x sub 2 minus a sub 12, a sub 21, x sub 2 equals to b sub 2, a sub 11 minus b sub 1, a sub 21, which can be solved for. So rearranging the equation, will be able to find the value of x sub 2. So a sub 11, b sub 2 minus a sub 21, b sub 1 all over a sub 11, a sub 2 minus a sub 1, 2, a sub 2, 1. So it is represented as equation 9.10. And equation 9.10 can then be substituted into equation 9.6. So it can be solved for the equation for x sub 1. A sub 2 to B sub 1 minus A sub 1 to B sub 2 all over A sub 1 1 A sub 2 2 minus A sub 1 to A sub 2 1. So, which is referred as equation 9.11. So, notice that equations 9.10 and equations 9.11 follow directly from Cramer's rules. So, you will notice the similarity of Cramer's rule to this function. The only difference is this is for our 2 by 2 matrix, so, or simply two linear equations. So, our previous example on our Cramer's rule, so we use the three equations, three unknowns. Example for elimination of unknowns. So, use the elimination of unknowns to solve the same equation as previously discussed in our graphical method. So, using the equation 9.11 and 9.10, so we will directly be able to calculate the value of x sub 1 and x sub 2, which is 4 and 3 respectively, without graphing it out in order to find their point of intersection, which is 4 for x sub 1 and 3 for x sub 2. So, which is consistent with our graphical solution. So, you can recall our figure 9.1. We can also use Excel in order to apply our elimination of unknowns. So, using Excel in applying elimination of unknowns, so with this given two equations, so for the first equation, we have 3x sub 1, 2x sub 2 plus 2x sub 2 is equals to 18 minus x sub 1 plus 2x sub 2 equals to 2. So, for our x sub 2, so the numerator, so same column, and we're going to use the values of B instead of values of A. So, you will notice the similarity in Cramer's rule. And for our denominator will be the determinant of the coefficient. So, which is 3, 2, 2, negative 1. And for x sub 1, so instead the first column, so we're going to use the values of B, which is 18 and 2. And for for the second column, it will be the values of 2. And for the denominator, we're going to use the matrix. So, the given matrices. So, we're going to find now the determinant. So, simply use mdeterm in order to find the determinants in Excel. So, we have 24 for the numerator. So, mdeterm. So, for the denominator. And we also have here mdeterm. And for our denominator, mdeterm. So, take note that your denominator should be the same because this is the determinant of the given coefficient. So, similar siya dapat. So, pareho dapat sila ng result. And x sub 2 for our x sub 2 and for our x sub 1. So, we will be able to find the value of x sub 2 and x sub 1. So, this is simply the quotient. We have here 3, and for the x sub 1, this will be 4. Able to find the point of intersection or the intersection of two lines without using graphical method. So, this is simply using the elimination of unknown, which is similar to the Cramer's rule. So, finding the determinants and substituting the columns with the values of B, depending on what values of X you'll be finding. Our next discussion is about naive Gauss elimination. This basic approach can be extended to large sets of equations by developing a systematic schemes or algorithm to eliminate unknowns and to back substitute. So, Gauss elimination is the most basic of these schemes. So, the general set of n equation will be represented in this particular set. This is just the same with our introduction about linear system. So this is the conventional form of the equations. As was the case with the solution of two equations, the technique for n equation consists of two-phase, the elimination of the unknowns, and solution through back substitution, as shown in the figure. So this is the two-phase Gauss elimination, forward elimination, and back substitution. The primes indicate the number of times that the coefficients and constant have been modified. So we have here the matrix form of the equation. So we will be able to find three unknowns. The forward elimination, this is simply eliminating part of our data. So this is simply using elimination or forward elimination. And for the back substitution, so we were able to find first the value of x sub 3 with the data, value of x at sub 3, so we'll be able to find x sub 2 and so on with our x sub 1. So in order to understand more of the process about naive Gauss elimination, have here an example. Use Gauss elimination to solve the given function or given three equations. So note, please use the original set of values to avoid round-off error. So solution, using forward elimination, so we can simply multiply equation 5.1 by 0.1 over 3 and subtract the result from equation 9.2 to give the result as this particular equation. Then we're going to multiply equation 9.51 by 0.3 over 3 and subtract it from equation 9.53 to eliminate. So, you will see here the solution process. So, this is forward elimination. Upon completion of the forward elimination, so x sub 2 must be removed to accomplish this. So, multiply equation 9.5.5 by, so negative 0.19 divided by 7.00333 and subtract the result. And you will notice we're now be able to apply back substitution. So, using back substitution, we were able first to find the value of x sub 3 and then the value of x sub 2. And finally, we were able to find the value of x sub 1. In order to check or to validate or verify, so simply substitute the calculated x sub 1, x sub 2, and x sub 3 to the three equations. They should have a result based on their b sub 1, b sub 2, and b sub 3 respectively. So, in order to understand the solution, we can use Excel applying the naive Gauss elimination. Based on the solution process, is first to rearrange the conventional form into matrix form. So, we already done that. So, we have the A and B values. So, the coefficient A and values of B. So, we have the coefficient matrix A and the values of B. B sub 1, B sub 2, and B sub 3. And forward elimination, the main purpose of forward elimination is to make the values at the lower triangle 0. Let's apply our Excel. So, we have here the value. So, same value, A11. So, let's just equate this. So, copy lang natin yung value. So, we already have the value of 3.1.2. 7.85. So, take note of the negative sign. So, you need to use the negative sign. And, for our elimination process, for the second row, in order to make 0.1 as 0, so row 2 minus row 1 multiplied by 0.1 divided by 3. This is simply row 2 minus row 1 multiplied by 0.1 divided by 3. And we're going to use this all for the second row. So, lalagyan natin siya ng dollar sign. So, manually, this is simply row 2 minus row 1 multiplied by 0.1 divided by 3. So, but we already used the dollar sign. We all know kapag hindi napapalitan or hindi natin kailangan baguhin yung cell dahil gagamitin natin sa entire solution, so we can simply use dollar sign in front if we're going to copy it horizontally. So, this is now the change value. So, you will notice the selected. So, we were already modified. Munang dalawa ang gagawin nating 0. So, we have here row 3 minus row 1, 0.3 divided by 3. So, we have here row 3 minus row 1, 0.3 divided by 3. We were able to modify and make these two as 0. Next is to make this 0 also. For the second modify, we're going to copy the first data and we're going to use the change value. So you will notice here there is a prime. So ibig sabihin, first modified values. And for our next value, we're going to use here the modified values. Paano natin gagawin? Para maging 0 ulit, we're going to use here second modify. Row 3 minus row 2 multiplied by negative 0.19 divided by value at R2 which is 0.0033 so on and so forth. So row 3 minus row 2 multiplied by 0.19 divided by 7.003. So, using dollar sign to avoid changes, copying the values. So, now we're able to make our triangle of our matrix to 0 values. So, this is what we call forward elimination. And for our backward elimination, rearrange. So, we will be able to find the value of x sub 3, x sub 2, x sub 1. Applying the given equation, this particular value divided by coefficient matrix at x sub 3 and for x sub 2, b sub 2 minus this particular data multiplied by the value of x sub 3 divided by the coefficient of x sub 2. Next, this data minus this multiplied by this minus this multiplied by this data and divided by 3. X sub 3 will be 7, x sub 2 is 2.5, and x sub 1 is 3. Continuing our discussion, we will now move to pitfalls of elimination methods. The first pitfall of elimination method is one division of 0. It is possible that during the elimination of back substitution phases, a division by 0 can occur. To round off error, it can become particularly important when large numbers of equations are to be solved. This is due to the fact that every result is dependent on previous result. Consequently, an error in the early steps will tend to propagate. That is, it will cause errors in subsequent steps. The solution process must use as much as possible the original result in order to avoid round-off error. And the next one is the ill conditioning system. So, small change in one or more of the coefficients results in similar small change in the solution. Alternatively, it happens when two or more equations are nearly identical, resulting a wide range of answers to approximately satisfy the equation. Since round-off errors can induce small changes in the coefficient, these changes can lead to a large solution errors. Next is singular system. When the two equations are identical, we would lose 1 degree of freedom and would be dealing with the impossible case of n-1, equations with n unknown. Such cases might not be obvious to you, particularly when dealing with large equation sets. So, the fact that the determinant of a singular system is 0, a computer algorithm can test to discern whether a zero diagonal element is created during the elimination stage. If one is discovered, the calculation can be immediately terminated and a message displayed alerting the users. Jordan elimination. Gauss-Jordan elimination is a variation of Gauss elimination. The major differences is that when unknown is eliminated in the Gauss-Jordan method, it is eliminated from all other equations rather than just subsequent ones. So in addition, all rows are normalized by dividing them by their pivot elements. Thus, the elimination step results in an identity matrix rather than a triangular matrix. Consequently, it is not necessary to employ back substitution to obtain the solution. So let's have an example of Gauss-Jordan elimination. So problem statement, use Gauss-Jordan technique to solve the same system as in example for naive Gauss elimination. For the solution, first express the coefficients and the right-hand side as an augmented matrix. So we need to represent this in a matrix form. Then normalize the first row by dividing it by the pivotal element 3 to yield this given equation. So the x of one term can be eliminated from the second row by subtracting 0.1 times the first row from the second row. Similarly, subtracting 0.3 times the first row from the third row will eliminate the x sub 1 term from the third row. Next, so it will be represented in this equation. Next, normalize the second row by dividing 7.00. And we will be able to get this particular function. So we are using here the normalization. Reduction of the x sub 2 terms from the first and third equation will give this particular solution. The third row, dividing it by 10.01, we will be able to have this particular equation. And finally, the x sub 3 term can be reduced from the equation, second equation, to give this function. So you will notice the diagonals have a value of 1. So x sub 1, x sub 2, and x sub 3. And for the lower and upper triangular, so we have the values of 0. So para mas maunawaan natin yung ating given example, we're going to apply Excel. Using Excel, applying Gauss-Jordan method. So we have here for our first modify, there is a similarity, but the main purpose of Gauss-Jordan is to make efficient matrix or this particular given matrix into this identity matrix. So for the first modify, in order to make the first element or the A11 into value of 1, so we're going to divide this equation into 3. So equation 1 divided by 3. This value divided by 3. And it will not be changed for the function. This will be the revised value of our equation 1. For the second or part of the first modify, we need to make this value as 0. So 2 minus 1 multiplied by 0.1 divided by 3. So 2 minus 1 times 0.1 divided by 3. And dahil hindi mababago ang ating data horizontally, for our, it will be row 3 minus row 1 multiplied by 0.3 divided by 3. Row 3 minus the row 1 multiplied by 0.3 divided by 3. Hindi mababago ang ating data horizontally. So, copying it out. So, this will be the revised function. For our second modify, we were not going to change equation. For our second equation, what we're going to do is to normalize this equation here, or the element here. Equation 2 divided by the value of 7.0033, so on, so forth. So, this will be applied here. So, 0 divided by this data. So, this is simply called normalization. For our third equation, we're just going to copy first the third equation. For our third modify, copy first and second equations. We're going to make this data as 0. So, row 3 minus row 2 multiplied by negative 0.19 divided by 1. This will be row 3 minus row 2 multiplied by negative 0.19 divided by 1. And, dahil hindi mababago yung ating selected, so this will be our data. So, for our fourth modify, copy the first and second. So, the revised equations or the revised linear equation, the first and second. And we're going to normalize the third equation. Equation 3 divided by 10.01204. Equation 3 divided by this particular data, dollar sign, copying, and we were able to normalize this equation. Next will be elimination process again. For our fifth modify, to make this data here 0. Row 1 minus row 2 multiplied by negative 0.033 all over 1. Row 1 minus row 2 times row 1 divided by row 2. And we're not going to change this data. So we have here the 1, so 0. So we were able to change this data. So copy data on our second and third linear equation. For the sixth modify, copy first and the last equation. We're going to make this 0. Row 2 minus row 3 multiplied by 0.04188 over 1. Row 2 minus row 3 times row 2 divided by row 3, which is 1. And hindi mababago ang ating data selected. We're able to make our second element as 0 for the seventh modify. We're going to copy second and the last equation. So what we're going to do is to make this value 0. Row 1 minus row 3 multiplied by negative 0.06806 divided by 1. Row 1 minus row 3 times 0.066 divided by 1 para hindi mabago ang data ng selected. So, using Gauss Jordan, so we were able to find the values of our x sub 1, x sub 2, and x sub 3 in a identity matrix. So,